Our next presenter is Yi-Tun Lin from University of East Anglia, typically plausible spectral reconstruction. So Yi-Tun, over to you.
Thank you, Mike. My name is Yi-Tun, and I'm a second-year PhD student at the University of East Anglia.
Today, the topic I'm going to talk
about. Sorry.
Yeah, if we just start again, because I'm just trying to get the ball down to you at the bottom of the list. Hang on.
Right.
I'm just going to move. Oh.
So the timer is going to restart.
No. You're fine. You're fine.
Now, I'll restart it. That's not a problem.
Yeah.
I can't get down to people. Oh, hang on. Because you're at the bottom of the list, my screen's not big enough. Apologies, everybody.
Just let me know when you're ready, Sarah.
Yeah. There we go, Lynn.
Okay. Cool. I can move my slide now. Okay. So my name is Yi-Tun. I'm a second-year PhD student, as I said before, at the University of East Anglia. And today the topic I'm going to present is physically plausible spectral reconstruction. So in spectral reconstruction, we'll try to get the radiant or spectral information from only the RGB or color information. And most of the time, this is formulated by machine learning algorithm. And in this study, we try to examine the physical plausibility of those algorithms, which means like whether or not the predicted radiance is going to adhere the physics between the actual radiance and the color. So why do we measure spectrum? As I show in the example on the right, three different objects having the same color appear to have very different spectral characteristics. So in terms of computer vision, this means that we can get the material properties at pixel level. And in terms of computer graphics, this means that we can use spectral imaging to characterize the object surfaces so that we can predict their colors under different illuminations. However, the recent technology has many drawbacks. So we want to reconstruct the radiant spectra using only the RGB data. So people from the machine learning study may tell you that this is very simple. You just give me a lot of matching color and spectral data, and I can train a model which does the job. Some recent methods like deep learning, deep neural network, or convolutional neural network is really complicated inside, so people refer them to a black box. You don't know what's actually happening inside, but it gives you the final answer. The problem here is like when we are training those black box solutions, we often forgot the simple relation between the radiant spectra and the color. So in an RGB camera, we have three different types of color sensors. Each can be described as spectrally varying sensitivity functions. So the colors are actually the weighted sum of the radiant spectra using those set of three spectral sensitivities. So we designed a very simple testing experiment. So from the ground truth RGB image, we recover the estimated spectra using the black box solution. And then we reapply the spectral sensitivities to see whether or not it reproduces the actual RGB image. The result is not quite. So the leading deep learning model gives us very significant color shifts. So if we think about the application in computer graphics, especially in artwork conservation, we wouldn't want to use a model which shift the color. So the problem here is like how we're going to make the existing model physically plausible. In a nutshell, our approach is to open three dimensions of the black box. We can represent the radiant spectra as n unknown points because we're studying spectral reconstruction, so those discrete spectrum are unknown. And these spectral sensitivities can act as the model coefficients, which gives us a physical system, which is the three-equation linear constraint. We want to make use of these constraints in the spectral reconstruction process. Well, sorry about the math. Here, we can represent the linear system as y equals a transpose x, where x is the spectrum and y is the color. With respect to this coefficient metric a, we can split the spectrum into two components, one spanned by the column space of a, the other part lies in null space of a, here I denote it as b. So what we need to know is like this a and b metrics are orthogonal. So using those information, we can essentially open the three dimensions of the box. Why? here we see like the coefficient A can be calculated directly using the RGB and the coefficient matrix. And whereas the coefficient B, we just rely on the machine learning techniques help us to figure out. So, using this model, we show that our method preserve the color fidelity during the spectral reconstruction process, and we advance the spectral accuracy of the state-of-the-art model. So this concludes my presentation today. I hope you enjoyed the talk. Thanks for listening.